Okay, so if you have recursive relation, and can we actually get this explicit formula so that you don't have to walk all the way up to that point? Just explicit formula, just one plug-in, and that's in general much harder than computing antiderivative, which is what we have focused recently. So next goal is that we can't find all the formulas at n, but this is somewhat is interesting part. If we have recursive formula or explicit formula, can you calculate the limit of a sequence as n approaches infinity? What happened to this behavior? And you can use it list plot command to see where it's actually going with the computer, but that only tells you up to whatever the computer can handle. This limit is not about when n is 1000 and 2000, right? When n is arbitrarily large, what is happening to that value? Computer will never prove anything to the eternity side of this thing. So that's our actual goal usually, but we need to study this one a little bit for those examples that works. So here's a limit of a sequence. I don't think it's a difficult concept. As we increase this index and we use a formula or recursive relation, what is happening to this value? Does that approaching L? And if it is so, then we call that as a limit of a sequence. AN is never equal to L. You agree? In general, A1 will never equal to L, right? But yet we use this equal symbol. It's because left-hand side is not AN. Left-hand side together with this limit notation is denoting that its ultimate place is approaching. Make sense? So that's what this left-hand side. Left-hand side is not AN. Is where's AN going? That's what left-hand side is. That place is equal to L. That's how you should understand. But we write it like this: AN approaches L. Often we drop this n approaches infinity because we understand that's usual context. But sometimes you have to clarify it. All right, so here's a new notation. AN is not L, but what do you see up there? Little arrow, like vector symbol, but that's my invention. Nobody used this notation, but it's clarifying a lot, many of the things. AN is not L, but one quantity that is approaching L. That's my notation for you. It's a behavior. And AN is infinity. I will allow that notation, but more people use AN is approaching infinity. AN is never infinity, but it is infinity. I look at it as a behavior. This one, AN is not L, and I put L arrow because it's approaching L, not exactly L, and here approaching infinity. So I'll allow this notation. So these are behavioral notation, and this is more people use more with this notation here. Limit of a sequence. Let me say this. This theory is about the limit of a sequence. There's nothing but just numbers, if you think about it, right? These are sequence of numbers. So if you put this in the place of mathematical structure, it goes to the really, really bottom of the mathematical foundation. There's no function or nothing. It's just about a number and how they behave, especially in infinitesimal way. So this theory really sits to really the bottom of the mathematical foundation. And if you really think about meaning of approaching and limit all that in a really, really mathematical sense, you really hit the bottom of this, like peeling the layers of an onion, and you end up in nowhere actually. So it really reaches a philosophical level of a mathematical argument. So this is pretty tricky, and let me explain it this way. When we say approaching, the word itself, I think, has kind of assumed some sort of motion, right? That's how we understand this approaching. But mathematicians will try to figure out the mathematical description of a continuous motion in physics in a mathematical way, and they realize that there's no way to do it. So they have to go back and make a foundation. They realize that this limits the idea they're describing must sit in the bottom of this reasoning chain. Then from there, we can explain something called the continuity in a mathematical sense, which is used for physical motion. And after that, differentiability, not derivative, it's not the right word, differentiability. That's a property in there. So when you're defining limits, you're not allowed to use the word approaching. Because what do you mean approaching? That seems like some continuously moving something. So what do you mean by continuous? Then you have to do the circular reasoning. So the definition of a limit became very, very esoteric and very, very mysterious. And that all happened again the period of Riemann. And because of the motion, the continuous change is not allowed. You will see in the mathematics book uses inequality instead of, okay, A is changing, then it must be this behavior or something. Nothing like that. They have to prove using inequality. So that's why you see a lot of inequality technique in mathematics. Try to avoid this idea of saying approaching, which is not rigorous in mathematics. We're not going to do any of this. We just accept this one. But I have to mention that this is where we are. This statement. So, limit laws of a sequence is about to introduce here. That why is this true? When you explain this, these limit laws are true. You cannot use the continuity at all. Something is changing. Then in that you cannot use the continuity, and that becomes tricky. So what they came up with is called so-called epsilon delta definition. This is something that we're not going to do. It's very strange way of defining, because it's sit in the bottom of everything is inequality here. There's nothing but this number is greater than less than that, and that's their definition. And you can interpret it as a continuous motion, but its statement itself, it does not involve any continuity and things like that. But we will just accept this one. But if you really like mathematics, you should think about this type of thing. Then you can kind of challenge yourself. Am I rigorous enough in my thinking? But these are the laws. If you have two sequences, think about order of operation. How are we going to understand that? This seems like an obvious thing, but you've seen this before, like limit laws. You've seen that in derivative rules, things like that. So order of operation, what you have to pay attention. You have a formula of an, explicit formula of bn, or you have a recursive formula of an, recursive formula of bn. What is the first thing you do is you add, subtract to come up with the explicit formula of the sum or the difference, or recursive relation for an and bn, right? Once you have that one properly defined or calculated using explicit formulas, then think about where does it go. And it is saying that if an is going A, bn is going B, then an plus bn, after you combine into one sequence, then they go to a plus b and a minus b. All right? I can use my, I hope I wrote this, right there, arrow notation that I invented to write this one neatly like this. If I have quantity that approaches A, right? That's what that an is, plus quantity that approaches B is supposed to be a plus b. The whole thing approaches target a plus b. That's the summary of that notation there. Okay? But what is the sensitivity here? Order of operation. That's what it's asking. Add first and limit later versus limit first, add later. This is limit first, your approach is A. So as if this limit is distributed over, what is it? Parentheses, distributed, right? So if you go there and then become A, if you go there, B. And if it's constant and multiply, it doesn't affect anything. Product doesn't affect anything. What about the quotient? One extra condition there, right? It should not approach 0. You've seen that before, probably. What happens if it approaches 0 and A approaches 1? Then it's going to be infinity. So let me write that down as my notation. Numerator approaches 1, okay? And denominator approaches, let's say, 0, which is this situation in here is excluded in that statement 4, correct? So what do you think it happens? A little tricky. If one says infinity, it's not fully correct. It's almost. Do you see that it can be also negative infinity? Approaching 0, you don't know if it's approaching from the right, from the left. If you're approaching from the left, that's actually a negative number, right? Think about negative 0.0001. That would be negative, 10,000, 1 million, things like that. So that's why they excluded it. That's how it behaves. Other than that, if it is not 0, then it goes where it is. And proving this one in the sense not using any physical intuition seems tricky to them, and they came up with this epsilon delta definition. And this is taught in advanced calculus, epsilon delta definition. So these are the some examples of a limit sequence. Before we enter that, I think I need to introduce this important thing called indeterminate form. These first two are quotient, right? First two are quotient. Both of them is excluded by that limit laws. The limit laws do not apply here. Third one is a product, right? One of them is approaching infinity. They're both supposed to approach numbers here, a and b. These are supposed to be numbers, not infinity. So that one is also excluded. Infinity minus infinity, that doesn't come from a minus b. A and b are supposed to be actual number. So that doesn't apply. One approaching and raised to infinity, that's a bit tricky, but that's also indeterminate form. And you probably met this one in the calculus 1. Okay, when you calculate the limits. All right. So here's what we're going to do. Why is this called indeterminate form? Is that not because it's undefined. 0 divided by 0 is undefined, right? 0 approaching 0 divided by approaching, they're always defined. None of them are exactly 0, right? All these quantities are all defined. Something really, really close to infinity divided by something really close to infinity, no problem with that. When you write down 0 divided by 0, that's a problem. That's undefined. But this one is not undefined. But we're saying it's indeterminate form because this information is not sufficient to conclude about the behavior of the combination of the other two behaviors. So I want you to come up with two examples that approaches infinity numerator, infinity denominator. Whole thing approaches something, 1, for example. And next example, this one also infinity, the other one infinity, but this time it approaches 2. Then I think that's a sufficient example. It's exactly the same situation. Sometimes you get 1, sometimes you get 2. Hence, it should be called indeterminate form. So let's begin that. Find exercise number 1. Find the pair for infinity divided by infinity. Infinity divided by infinity is defined, but its limit is not. Maybe it's just not enough information. That's why we call it indeterminate form. Do you understand what I mean by pair? Not this one and that one. It's not that. You have to compute first an, bn, and you consider an divided by bn. Second, this is another pair. an, bn, different an, bn, such that an, bn divided by, they go somewhere. But these two things are different, but they're all approaching infinity. Numerator, denominator, both cases, they're approaching infinity. But this one goes to 1, this one goes to 2, for example. Okay? That's what you have to find. All right, is this first example fair enough? N is approaching infinity, and n is also approaching infinity. So it's actually infinity divided by infinity. But it's actually a lot simpler than that, n divided by n. So it's not only is approaching 1, it is actually 1, right? So if you want to make it 1, I think probably it's more interesting if you change it to that, n divided by n plus 1, then it is actually approaching, not the flat to be 1. Can someone explain why this n divided by n plus 1 is approaching 1? Here's a situation. You put yourself in a situation you're explaining to someone who don't understand why this one is approaching 1. That's probably clarify what I'm asking. Usual technique that's introduced here is that you divide everything by 1, n, so it is n, 1 plus 1 over n, right? Numerator and denominator divide by n, and that's, if we divide by n, sorry, this is supposed to be 1 there, right? So limit law says is always 1, it's there, and is always 1, it's there, right? What about this one here? 1 over n? That's pretty clear that the approach is 0, right? 0. Limit law says this whole thing 1 plus 0, it is not 1, but it's 1 arrow, a quantity that approaches 0. Number 4, the limit law says if it is like this, numerator flat 1, denominator is approaching 1, non-zero, then it is approaching 1 divided by 1, right? So that's why. That's one reason. Or you can interpret it as a x divided by x plus 1 and put the limit x approaches infinity. Here I switched from n to x, allowing x to be all real numbers, not just integers. Right? If you were asked this question in the Calc 1, what would you do? What technique would you do to calculate this limit? There's some French guy, some sort of type of rules that you can apply it here. Looks a lot like a quotient rule, but it's not a quotient rule. It's L'Hopital's rule, right? So limit stays there, but strange, you differentiate numerator and denominator separately. It's 1 and it's 1, right? And if this limit makes sense, then that happened to be the answer. That's called L'Hopital's rule. Powerful rule if the factors involved in here are differentiable functions. If it's arithmetical function for which differentiability is ridiculous to consider, then you have to use different technique. But a lot of examples differentiable, L'Hopital's rule is one thing. All right, what is the second example you can come up with now? AN should be what and what, so that you get something different. Maybe 2n and n plus 1. Would you believe that works? That one goes to infinity, right? I'm sorry, that. To rewrite that. 2n divided by n plus 1. That one goes to, that one is infinity divided by infinity. It's a behavior, but if you again divide everything by n, here's a 2, and here's a 1, and still there's 1 over n, right? So where does it approach? Which is actually 2 divided by 1 plus 0 bar, 0 arrow, therefore it approaches 2 divided by 1, so it's 2. Okay? So what is the point of these two examples? Indeterminate form. Why is it called indeterminate form? This information here is not sufficient to conclude what is happening to that. Sometimes 1 and sometimes 2. Correct? Can you come up with an example that is approaching 0 divided by approaching 0, which is why you should call indeterminate form? That's your second exercise, right? So here, exercise number 2, find the pair of examples, that's what I should clarify, for approaching 0 divided by approaching 0. Right. 1 over n is the simplest example I think I can come up with. And there's and then 1 over n divided by 1 over n plus 1, and here's the algebra. You conclude it's a 1, and second example here, and it concludes 2. Again, both are the situation that approaching 0 divided by approaching 0 divided by approaching 0, you end up with different behavior. Hence it's called indeterminate form. All right? So here's a harder example. No, approaching 0 is tricky. All right, so let's look. Any question about the indeterminate form? Let's look at it. And here, can somebody come up with this infinity times 0, approaching 0 example? Let's think about that. What was the example of 0, approaching 0? 1 over n, right? What was the example of infinity? N, if you multiply it, always 1, right? Well, you can throw in any coefficient in here, don't you think? And it does not change its behavior. And therefore, you end up at a different number. Infinity minus infinity, I think, is a trickier. No, it's not that tricky, right? It's not that tricky. It's n plus 2 minus n, or n minus n. They're all infinity, but difference is always constant. So it's also indeterminate form. Make sense? Why should I talk about that right now? Probably no, I don't know. Right, today there's no AP, remember? It's Tuesday. Yeah. All right, here's the thing, the next one. This I find is a bit harder, 1 to infinity. And it's actually a famous example. Do you agree that inside 1 plus x that approaches 1 as x approaches 0, right? And what about the the exponent there? As x approaches 0, that approaches like positive infinity or negative infinity, depending on where this one's going, from the right or left. And what happened to that particular example? It's e. Remember E, 2.7, right? That was actually the most standard definition of E. What is E? And this is how E is defined. All right? So that's a strange example. Let me go back to the form. 1 raised to infinity. Anything that raised 1 to something, they're supposed to be 1, right? Anything that is slightly greater than 1 raised to infinity, if you think about it, 1.1, keep multiplying to itself, it grows. Try to go to infinity. So it's two different forces involved. This guy, infinity, try to pull that up to infinity. The base 1, it tried to stay in 1. So two different forces. Settle on where? Some position, equilibrium position, called E. Right in between, right? This is, people believe it came from Euler, not equilibrium position. All right, so that's very strange and very important example. E appears everywhere in science and mathematics, especially where the differential equation is. But with the arrow notation, 1 plus x raised to 1 over x fall into 1 raised to plus minus infinity. That's indeterminate form. Now we have to come up with one more example that's different, right? And you can throw in 2x and things like that, and then it becomes a 2x and e to the second, and it changes easily. You will see a lot of these example variation, right? These are called what? Indeterminate form. If you're taking, have finished the Calc 1 courses, you should be able to recognize this indeterminate form and never write, 0 divided by 0, undefined. That shouldn't be happening anymore. All right? Any question before we move on? All right. Let's see what kind of example I have it there. All right. These are limits of sequences. And you say AN, right? Is it an indeterminate form, or we can use limit laws? Limit laws, indeterminate form. Which one is it? Numerator? What's happening to the numerator? Infinity, right? What happened to the denominator? Also go to infinity. Limit laws or indeterminate form? Indeterminate form. You can't use limit laws here. But if you algebraically manipulate this one, and all of a sudden you can use limit laws. That's what we're doing. So what manipulation do you see for part A? Divide numerator and denominator by n cubed, and then you're going to do it. Similar example. So what is the answer? Limit of this one is, you see the 3? They kind of 1 over n cubed. The answer is 3. What's the observation? If you see polynomial of degree n divided by another polynomial of degree n, then what's going to be the answer? An is one polynomial of degree n, degree something, and there's another polynomial, degree n. Good news, no partial fraction decomposition is involved in this problem. Just look at the leading coefficient, right? What is the leading coefficient of p divided by leading coefficient of q? Under what condition? If what is equal to each other? The degree of a numerator is equal to the degree of the denominator. Do you see that's the case here? N cubed. Then all that matters is those leading coefficients. So 1/3, that's the answer to that one. Right? But do you think you can explain this one? Why this one works like this? The technique is the same. You divide the numerator and denominator by that highest power, and everything else approaches 0. Only these leading coefficients survive. But these are differentiable functions. So what other techniques can you use for this guy? Keep differentiating numerator and denominator separately, right? So how many times should I differentiate this guy to get rid of n cubed? 3 times, right? How about this one? Exactly the same 3 times with this n cubed in there. The 6 and 6, do you know where the 6 is coming from as you differentiate n cubed? 1 time 3 comes down, second times 2 comes down. So those 6 cancel and leave 3. That's L'Hopital's rule. Okay? What if it's different? What if it's degree 2? What do you think that's the answer? Degree 2 divided by degree 3? What is this one in here? In this case, if degree of a numerator, p, is smaller than the degree of a denominator, q, right? Approaches 0, right? Why? L'Hopital's rule, or divided by the highest power both sides, and you'll be able to conclude numerator approaches 0 while denominator approaches non-zero. That limit law applies. Things like that. What if it's the opposite? What happened to an? Polynomial divided by polynomial? If degree of a numerator, p, is greater than the degree of a denominator. Like n over 1. 1 down there is a constant, right? N up numerator is degree 1, so that's the case. And we know that particular example goes to infinity, right? But you can also argue that in general they go to infinity. So one way is that L'Hopital's rule is not pretty nice here. So one explanation is that let's say n squared, n cubed. You do the same thing. You divide. That's not the case. N cubed here. That's an example where the numerator is a high degree, and you factor out n, and you can see there's n there, and everything else has an n in the denominator, so they approach 0, and because of the same degree now, they approaches 1. Inside here, they approach 1, while n approaches infinity. So this is infinity times approaching 1. That is approaching infinity. All right? Various many different ways to argue this one. But it's something that I can assume that you can handle this one, right? Polynomial divided by polynomial, you can do that really quickly now, right? So hard thing is this second guy. So who has an idea about this one? First of all, is this indeterminate form or something else? What happened to the base here? It is approaching 1, don't you think? Because it's polynomial divided by polynomial. So leading coefficient 1 divided by leading coefficient 1, correct? So on the base part is approaching 1. How about numerator? I mean, not numerator, the base part, exponent part. It's approaching infinity, right? Was this one of the list? In the list? It's an indeterminate form, right? So how do you calculate this one? You have to enter that definition of E because it's somewhat in that shape. Don't you think? Okay, let's enter that. You have to manipulate that 5 plus n divided by n into 1 plus x. That's the goal. What is my x? Right? Okay, let's look at that. Here. That's E. Whenever I pull this expression, I can call that one E. And that's the technique. All right? You recognize that. All right, I recognize it. It is approaching 1. So can I just call it like 1 plus whatever if it is approaching 1? Right? So what do you see? The left-hand side, is that 5 over n plus 1 equals 1 plus x? Now it's clear what your x is, right? What is x? 5 over n. Now once you know the connection between x and 5, the next thing you have to write everything here in terms of x, correct? So let's do that. Bn is 5 plus 1, this is now known as, what is 1 plus x? Is that okay? We set that inside 1 plus x and figure out what x should be. Is that correct? So what should I do to the exponent? This is now n, but how do you write this one in terms of x? Here. That's the connection, right? What is n? 5 over x, so you can replace that with the 5 over x. Now everything is in terms of x. We know what happened to this guy. 1 plus x raised to 1 over x in a reciprocal power like that, and they approach e. So let's isolate that part if possible. Do you think you can isolate that part like this? 1 plus x, 1 over x, like that. What should we do to that one to make this one two things equal? raise the entire thing to what power? Fifth power. Now limit law applies. If inside approaches e and outside is always 5, then continuity actually approaches. And so that this becomes what? Approaching e, right? Raised to what power? Flat 5 power. This is actually that. Is equal to that number, then it's approached e to the 5th. You take out your calculator and or Mathematica and calculate the where is this approaching and compare that number with e to the 5 is the 5th, and then it must be correct. Okay? That's the trickiest one. How about n to the n approaches infinity, right? 1 over n approaches 0. That's another indeterminate form. So, do you know the technique for this guy? Most satisfying one is that this identity, so recall, some point of your life you have seen this one, even if you don't remember. A to the b can be written in terms of e. You know that? To the e. Right? Anything, any number, you can put it up there like this, don't you think? Because e and ln cancel each other. That's inverse function, right? You do ln first, then e later, what happened? It cancels and just becomes a to the b. This is obvious statement. But if you pull that b down because of the ln, then it gets interesting. This statement, a to the b, is equal to e to the something where there's no, you don't expect any n is involved in it here. E is just a flat number. You kind of isolated this exponent and base nicely, separated it. That's what this one just did. So you can write it like this. N raised to 1 over n is e to the what? E to the ln of n raised to 1 over n, correct? And what happened to that exponent here? Comes down to this level and write ln of n. Now whole sequence was separated and nicely isolated, right? So it's all about this guy here. So let's write down what happened ln n divided by n. Where does that go? Indeterminate form or not? I'm going to work on this exponent first and come back in here and just stick that number in there. That's the limit law. Extended version of limit law, or continuity of the function e to the x, whatever we want to use. So, any idea about ln divided by n? Yeah, both approach infinity indeterminate form. So what are you going to do? ln and polynomial, they don't algebraically mix well together. It's transcendental function, right? But they're differentiable. So what do we do? Rule? L'Hopital's rule. So what is the derivative of the numerator? 1 over n. What is the derivative of the denominator? 1, right? So this became 1 over n. Again, they're not equal. They're not derivative of one another. L'Hopital's rule says you can, if you want to compute the quotient form of indeterminate form, calculate its derivative and take the quotient. They're going to approach the same number. So where is this one approaching? 1 over n. Approaching 0, obvious, right? So what happened to the numerator? They're approaching 0. That's what we covered. So you can write it like this. It's equal to 0, e to the 0 arrow. E is fixed and exponent is the quantity approaching 0. So therefore, this must approach e to the 0 by the continuity of a function e to the x. But that continuity really involves the proof of this statement itself. So we should really call the correct reasoning of the final bit of extended limit laws that still holds along with this standard function. Those are 3 examples here.